So now we know the phenomena of interference. Using transverse wave nature or longitudinal wave, we can produce the interference. Interference of sound wave is possible, interference of light wave is also possible. We are studying the interference of light. In optics section, we are considering the interference of light. So we know the definition, we know the types of the interference, we know the nature of the interference pattern, condition of path difference, condition of phase difference, all part we have seen. Now, to demonstrate the phenomena of interference in laboratory, there are so many experiments available. Out of that, two experiments are included in our syllabus. One is this Young's double slit experiment, short form Y.D.S.E. MCQ problem मध्ये आता short form Y.D.S.E केलेला असतो. And second one is a Fresnel's biprism experiment. It is suggested by the scientist Fresnel. It is suggested by the scientist Young. Their names are given. We know about the Young. Young has given the some modulus of elasticity. Young's modulus. The name is given Young's modulus like this. Now let us see this Y.D.S.E. So first we will see the experimental arrangement, experimental setup. So the experimental setup is like this. Here we are using the plane wavefront, and we know that plane wavefront is obtained by this method. Suppose this is a convex lens of short focal length. At the focus of the convex lens, a point source is kept, so it will produce spherical wavefront, diverging spherical wavefront. So these are the rays starting from the source and they are incident on the convex lens L. Now, since the source, the object is at the focus, we know that by the property of the convex lens, the emergent ray will be parallel, like this. So when the rays of light are parallel, then the wavefronts are plane. So this method we know. Spherical wavefront, incident spherical wavefront is converted into the emergent plane wavefront. Spherical wavefront is converted into the plane wavefront. So these are the wave normals which are parallel. So this is a plane wavefront. Now this plane wavefront is incident on a screen having two slits. So this is the screen, like this. It is having two slits. Say one slit is here and other slit is here. So S1 is a one slit, S2 is a another slit, like this. So in this case, S is a primary source, S1, S2 are the secondary sources, and they are obtained from one and the same Woodland source. Therefore, S1 and S2 be held as the coherent sources. Now, it is a rectangular slit. S1 and S2 are the rectangular slit. So we know that when the source is extended like a rectangular narrow slit, it produces the cylindrical wavefront. So this experimental arrangement is perpendicular to the plane of the blackboard, plane of the paper, and therefore the cylindrical wavefront are like this. Cylindrical wavefront increasing radar. So here we can show by circles like this. So these are the cylindrical wavefront. So ही पुढची फिगर आपण मागे जी काढलेली तशीच आहे ही. This is the position of, say, trough. So this is the circle of crust. This is the circle of crust. Then circle of trough. Circle of trough. circle of crust, circle of crust, like this, circle of trough, circle of trough. So these are the points of construct intervals. इथे दोघे डॉटेड डॉटेड सर्कल क्रॉस होतात. सो टू ट्रफ क्रॉस इच अदर constructive intervals. Two crush cross each other constructive intervals. Constructive intervals. On this side there is a screen. This screen is denoted by AB. This screen is denoted by PQ. These two screens are kept parallel to each other. So this is a maximum intensity. All the points on this line are having maximum intensity. So this will be a bright band. Now this is also the point of constructive interference. Point of constructive interference like this. So this is the another bright band. On above, this is constructive interference, point of constructive interference. So this is also bright band. Now here one crust and one trough cross each other, so it is a point of destructive interference. Point of destructive interference. So if you join them, then this will be a minima, means dark band. Similarly on this side, if you increase the circle, this will be the what more minima on this side. This is destructive interference, point of destructive interference, minima, like this. So this is the interference pattern. So maximum means bright band, dark band, like this. So maximum means bright band, alternate bright and dark bands are observed. Bright, dark, bright, dark, bright, dark. So this is the nature of the interference pattern, like this. So this is the experimental arrangement, Young's double slit experiment, like this. So we can describe the experimental setup like this. A monochromatic source S this is kept at the focus F of a convex lens L. Therefore, the emergent wavefront is a plane wavefront. A screen AB having two narrow rectangular slits S1 is kept in front of lens, so that SS1 is equal to SS2, and therefore the phase difference between S1 and S2 is constant equal to 0 degree. Therefore, S1 and S2 are monochromatic and coherent sources. So this is a necessary condition for obtaining the steady interference pattern. So the two sources must be monochromatic. Now why they are monochromatic? Because this source is monochromatic. So the wavelength is lambda here. So this is also wavelength lambda. This is also having wavelength lambda. So same frequency, same wavelength, and constant phase difference. These are the conditions for they are obtained from one and the same original source, like this. So S1 and S2 are monochromatic and coherent sources. Now these are the cylindrical wavefront. The cylindrical wavefront as shown in the figure. The cylindrical wavefront emerging from S1 and S2 cross each other on the screen PQ and produces steady interference pattern which consists of, we know the nature of the interference pattern, which consists of alternate bright and dark bands, which are sharp, clear, easily distinguishable, like this. So this is the experimental setup. Observations. So the nature of the interference pattern we already know. The points where circles of crust actually they are spheres, circle of crusts or troughs from S1 and S2, from coherent sources S1 and S2, superimpose we observe bright band shown by hollow circle. येथे हॉलो सर्कल आपण दाखवतो. The points where one circle of crust and other circle of trough, other circle of trough superimpose each other. Superimpose each other. We observe minimum intensity. We observe dark band, and therefore we observe the nature of the interference pattern like this. The steady interference pattern consists of alternate bright and dark band which are sharp, clear and easily distinguishable like this. So we can demonstrate the phenomena of interference of light by using this simple arrangement. Now, what is the importance of this experiment? Importance of Y.D.S.E. Actually, interference phenomena was theoretically explained by Huygens wave theory, but the experimental proof verification was given by this experiment. So this is the first experiment to demonstrate the phenomena of interference. So the importance is like this. This is the importance. First experiment to demonstrate practical proof to demonstrate the phenomena of interference of light. Interference of light. Second, it confirms the wave nature of light. This experiment confirms first experiment confirm wave nature of light. Wave nature of light. Huygens फक्त theoretically सांगितलं होतं, this wave nature can be used to explain the phenomena of interference, but it was proved experimentally like this. So third, it is used, even though nowadays we can use this experiment, it is used to determine the wavelength lambda of monochromatic light used. Monochromatic light used in the experiment. So these are the 3 points of importance. It was the first experiment to demonstrate this phenomena. मोनोक्रोमॅटिक आणि कोहरंट सोर्सेसची आयडिया यूज करून नंतर खूप एक्सपेरिमेंट इंटरफेरन्सचे सांगितले गेलेले आहेत. इट वॉज द फर्स्ट एक्सपेरिमेंट. देन इट कन्फर्म द वेव्ह नेचर ऑफ लाईट. दिस इज द एक्सपेरिमेंटल प्रूफ फॉर वेव्ह नेचर ऑफ लाईट, अँड we can use this experiment to determine the wavelength of the monochromatic light used accurately. Determination of wavelength is very accurate. So what is the formula for lambda that we have to see in the theory of interference band? That theory of interference band is nothing but again the same arrangement, experimental setup used for Y.D.S.E like this. Now using the arrangement experimental setup of Young's experiment, we have to explain the theory of interference bands. So theory of interference bands is we have to determine the position of the bright and dark band. On the screen PQ in the last figure, we observe alternate bright and dark band. So where the bright band is observed, where the dark band is observed, and on what factor does this position depend, that we have to see. So for that purpose, we are using this type of arrangement. Suppose This is the screen AB. This is the screen CD. They are kept parallel to each other. CD screen is used to observe the interference pattern, and AB is used to produce the two monochromatic and coherent sources like this. So this is slit S1. This is another slit S2, and this is the center of the two slits O. So these two slits are separated by a small distance d. The two screens are kept separated by distance capital D. Draw perpendicular from O to the third screen. So this is O dash. O dash is the center of the screen. Now draw two more perpendicular. This is the geometry that we are adding. O dash, S1M, S2N, R. The perpendiculars on screen CD. Where we observe the interference pattern. So S1O is equal to S2O is equal to DE by 2. This is therefore this is D by 2. So if this is D by 2, this is also D by 2. This is also D by 2. So this is also equal to MO dash is equal to NO dash. So O dash is a perpendicular bisector of S1 S2. आणि हे perpendicular bisector म्हणजे हा angle 90 degree. Now we have to find the expression for the part difference. So we know the meaning of part difference. It is the difference between the distances covered by the two waves when they cross each other at a point. So in this case, we will consider the point of crossing anywhere on the screen. So that point we are considering as a P. And this P point is at a distance y. O dash is considered as the center. O dash is the center of the screen CD. Let P be the point of observation at distance y from center O dash. Therefore, y is equal to O dash P. So small d and capital D, they have meaning like this. D is equal to S1 and S2 is equal to distance between two coherent sources. Capital D is equal to distance of the screen of observation from plane of coherent sources S1 S2. This is the screen used for observation, and this is the plane of the two coherent sources like this. Now lambda is equal to wavelength of monochromatic light used here. Monochromatic light used here. So we have to find the particles. So join one ray of light from S to P1, another ray from S2 to P, like this. So what difference at point P? At point P, what difference? What difference PD is equal to S2P distance is larger than S1P. So this is the equation small a. This is the equation 1. Now we have to find this S2Pu minus S1Pu in terms of Y, D and D, like this. And for that purpose we have to use the simple geometry. So in this figure, there are two right angle triangles. One is S2NP and other is S1MP. So first we will consider this triangle. So in triangle S2NP, by Pythagoras theorem, S2P square is equal to S2N square plus NQ square, NP square. This is NP, and therefore this is equal to S2N is D square. And now what is NP? NP is equal to this OP plus ON dash. So this is equal to Y plus D by 2 whole bracket square, and therefore S2P bracket square is equal to D square plus Y square plus 2 times Y into D by 2 plus D square by 2. This is equal to 2. Now consider this upper right angle triangle S1MQ. This angle is also 90 degree. So this is also right angle triangle. So in triangle S1MP, again we will use the Pythagoras theorem. S1P square is equal to S1M square, this is D, plus now MP square, but MP is equal to, फिगर मध्ये बघा MP ची व्हॅल्यू काय, but MP is equal to OP minus OM, and therefore MP is equal to Y minus D by 2, and therefore S1P square is equal to D square plus Y minus D by 2 whole bracket square is equal to D square. Now expand this, A minus B bracket square, Y square minus 2 into Y into D by 2 plus d square by 4. This is equation 3. So this 2 will get cancelled, this 2 will get cancelled. So 2 minus 3 gives 2 minus 3 gives S2P square. This is the simple mathematics. You can also give the value directly. S1P square is equal to, this is d square plus y square plus yd plus d square by 4 minus d square minus y square minus plus yd minus d square by 4. So the d square will get cancelled. So this is nothing but only 2 times yd. This is a simplification. Right hand side is only 2 times yd. Now factorize this. So this is equal to S2P minus S1P, x minus y, x plus y. And therefore we have to find the value of this. Part difference at point P between the two values is equal to S2P minus S1P. So we have to find this value, and therefore we will keep this value on this side. S2P minus S1P is equal to 2 times yd upon S1P plus S2P. Say this is equation. We have given the number like this. This is equation A, this is equation B, this is equation. So A minus B will resolve. This is equation C. This is equation C. Like this. आता ह्या इक्वेशनमध्ये अजूनही डिनॉमिनेटरला S1P आणि S2P बाकी आहे, तर ते आपल्याला सिम्प्लिफाय करायचे. फिजिक्समध्ये त्यासाठी आपण ॲप्रॉक्सिमेशन यूज करत असतो. व्हॉट टाइप ऑफ ॲप्रॉक्सिमेशन इज यूज? तर असे ॲप्रॉक्सिमेशन आपण फिजिक्समध्ये बऱ्याच वेळा यूज करतो. वेन theta is very very small, then sin of theta is nearly equal to theta in radian, tan of theta is nearly equal to theta in radian. When time is very very small, then the arc AB of the circle is considered as a straight line like this. So this is also one observation. What is observation? When the screen used for observation of interference pattern is taken very long distance away, then D will increase. Very long distance away, then we can use this approximation. When the screen CD is taken to a long distance away from AB and point P, is very close to center O dash of the screen CD. That is, mathematically you can like this. When D is very very much greater than Y, this capital D, and D is very very much greater than small d. Small d is a distance between the two coherent sources. So sources are close to each other. The point P is very close to the center. So under this condition, Distance S1P is nearly equal to capital D. Distance S2P is also approximately equal to capital D, and therefore S1P plus S2P is nearly equal to 2 times D. D plus D is equal to 2 times D. Therefore, equation C gives S2P minus S1P is equal to 2 times Y.D. upon 2 times D. So that is equal to Y D upon D. Therefore, path difference at point P is equal to Y into D upon D, where Y is the distance of the point P from the center of the screen used for observation. So this was basic value S2P minus S1P, and in terms of Y, D and D we have proved like this. So this is the expression for the path difference in terms of Y, D and D. D is the distance between the two coherent sources, capital D is the distance between the two screens, distance between the plane of the two coherent sources and the screen of observation or interference pattern, and Y is the distance of the point P from the center. O dash is considered as the center, it is considered as a reference point. जसं आपण ग्राफवर ओरिजिन रेफरन्स पॉईंट घेतो आणि बाकीच्या पॉईंटचे डिस्टन्सेस आपण तिथून मोजतो, तसंच हा पण प्रकार येतो. नाऊ we know the expression for the path difference only. Now what to see the position of the bright and dark band. So for bright band we know the condition of path difference. Path difference is equal to even multiple of lambda by 2, and for dark band path difference is equal to odd multiple of lambda by 2. So by combining this condition with equation 2, we can get the position of the bright and dark band like this. So this is the mathematical part. The question can be asked like this: derive the expression for the path difference in terms of Y, D and D where the symbols have usual meaning. So here we are using the arrangement of the Young's experiment. So this is the screen where the two coherent sources S1 and S2 are used in the form of narrow rectangular slit. This is the screen CD where we observe the interference pattern like this. So through S1 and S2, monochromatic waves are coming out and they cross each other at point P. So at point P, the path difference between the two waves arriving at point P is equal to S2P minus S1P. S2P distance is more than this. Now we have used geometry between the two screen AB and CD. We have drawn three perpendicular OO dash, S1M and S2M. OO dash is a perpendicular bisector. OO dash is a perpendicular bisector of S1 S2. So it is perpendicular to S1 S2, and this angle is 90 degree, and distance S1O is equal to distance S2O. So the two coherent sources are separated by a small distance d, and therefore this S1O is equal to S2O is equal to d by 2. Now these two are perpendicular, so distance between the two parallel remains same. So this is d by 2, therefore this is also d by 2. This is d by 2, therefore this is also d by 2. So on the screen the various distances are like this. Now P point of observation where we have to find the path difference. It is at distance y from the center O dash of the screen. So y we know distance of the point of observation from the center O dash. D is the distance between the two coherent sources, and capital D is the distance between the plane of the two coherent sources S1 and S2 and the screen used for observation of interference pattern. So we have to find the path difference at point P, and it is given like this: y into d upon d. So this is only the Pythagoras theorem. So by Pythagoras theorem in triangle S2NP and S1MP we get this relation. So here we have used the approximation. याचे ॲप्रॉक्सिमेशन आपण फिजिक्स अँड मॅथमध्ये बराच यूज करतो. द स्क्रीन सी डी इज टेकन टू ए लॉंग डिस्टन्स, देअरफॉर डी विल इनक्रीज. So D is very much greater than distance between the two coherent sources. The sources are kept close to each other. The point P is at very close to the center O dash, therefore y is very very small. Generally this d is in millimeter, y is also in millimeter, and but d is in meter, more than 1 meter. Therefore when d is very very much greater than y, when d is very very much greater than small d, then S1p and S2p, these two distances are nearly equal to capital D, approximately equal to, therefore this is called as a approximation, like this, and therefore finally we get this relation. So part difference at point P is given by y into d upon d, like this. Now let us decide the position of the nth fragment. Position of nth right band. Let yn is equal to distance of nth bright band at point P on the screen CD. Therefore, for nth bright, therefore part difference at point P is equal to same formula, yn into d upon d. So this is equation 1. हा फॉर्म्युला आपण डायरेक्ट घेतलेला, फक्त इथे सफिक्स आपण ऍड केलेला आहे. Here we are observing the nth bright band. So part difference at point P is equal to yn. The meaning of yn is this: distance of the nth bright band at point P on the screen from center O dash. Center O dash. Now the point P will appear bright when part difference at P is even multiple of half lambda. Therefore part difference at P is equal to PD is equal to 2n multiplied by lambda by 2 or n lambda. This is equation 2. So for nth bright band, this equating these two values we get like this. Therefore equating 1 and 2, part difference at point P is equal to yn into d upon d is equal to n lambda, and therefore yn distance of the n bright band is equal to n into lambda into capital D upon small d. So this equation gives the position of the n bright band is given like this: n into lambda into capital D. So this is equation capital E. ऍक्च्युली ह्या इक्वेशनचे दोन युजेस आहेत. जर आपल्याला yn माहिती असेल तर आपण अननोन व्हेरिएबल लॅम्बडा काढू शकतो, लक्षात. सो दिस इज द इक्वेशन like this. Now in the similar way we can find the position of nth dark band. Let Yn is equal to this distance of nth dark band at point P on screen CD from center O dash of the screen. Therefore, by using this formula, part difference at point P is equal to PD is equal to distance of the P point into small d upon capital D. Say this is equation 3. Equation 1, equation 3. Formula 2 है. Now at point P we observe nth dark band if part difference at P is equal to odd multiple of lambda by 2, and therefore part difference is equal to 2n minus 1 lambda by 2 or n minus half lambda. This is equation 4. So equating 3 and 4 we get part difference at point P is equal to Yn into d upon d is equal to n minus half lambda, and therefore Yn is equal to n minus half into lambda into capital D upon small d. So this is equation B. Equation A gives the position of the nth bright band. Equation B gives the position of the nth dark band. Equation B gives the position of nth dark band like this. So we can determine the position of the where we will observe the n bright band, where we will observe the n dark band. That is decided by equation A and B like this. But for that purpose we should know the wavelength of the light used, we should know the small d distance between the two coherent sources and capital D distance between the plane of the two coherent sources and the screen of observation like this. So in this way we can find the position of the n bright band and n dark band if the distances are known. Okay, we will stop here. Next time we will see that whether the bands are equidistant or not. They are equally spaced, they are very close to each other, etc.